Good afternoon, friends. This is Mechanical Vibration Lectures 3. Today's lecture is about undamped free vibration analysis of single degree freedom system. So we are going to see undamped free vibration. What are the objectives of undamped free vibration analysis? We can see one by one. Okay, we can see this is the type of this type of oscillation. Okay, the spring is suspended on a rigid ceiling, and the mass is suspended on the spring, and the spring is attached to the rigid system, so that the spring is free to vibrate due to only the given initial excitation for the mass. Okay, as you see from this diagram, it is continuously springing, vibrating. That is, here the only thing given is the initial excitation. That is in the form of displacement or in the form of velocity. So you can observe it. Okay. So this is the type of system. For example, if we take a spring which is in unstretched position, this is a spring in its original or unstretched position, and whenever we hang the mass on the spring, including the mass, it will go to some equilibrium position at the very beginning. Here it is in the equilibrium position. In this position, we have mg minus ks is equal to 0. That is static deflection. We have some static deflection s. Okay, the initial anxiety is there, and due to the addition of mass, it goes to some static equilibrium position. So that is deflection, that delta L, which is s. So the equation of this system is mk minus mg minus ks, which is equals to 0 from the sum of force calculation. And then when we further disturb the system from its equilibrium position, the mass will oscillate. In actual case, this mass oscillation is not like what we are observing from this picture. It will, after sometimes, it will come to this static equilibrium position. But in ideal case, we are talking about free vibration. When we talk about free vibration, there is no damping, that the system is out of damp. Even we disregarded the air friction, and all damping systems are disregarded from this system. So that is the meaning. And this deflection or the oscillation of the mass about its static equilibrium position sometimes goes back to the extreme point, and it goes down to the extreme point. So it will vibrate like this. So this kind of motion is called a simple harmonic motion type, or free vibration case. Okay, so the learning objective of this type of analysis is from the very beginning, driving the equation of motion of the single degree of freedom system using suitable techniques. We have a number of techniques to drive equation of motion. We can apply Newton's law. That is, it can be actually not only Newton's second law, but Newton laws are all helpful. We can also use D'Alembert's principle, or there is a virtual displacement principle. That means energy conservation principle, and other cases are also be applied to drive the motion equations. So The next is to solve the free vibration equations of single degree of freedom with and without damping. Actually, when we consider with damping, that is damped vibration case, but what we are going to see is undamped vibration. So that is that doesn't include the we'll see in the next lecture that damped vibration case. To solve spring mass damper system. So when we consider this spring mass damper, then it is damped vibration case. That is the next day the next day lecture. Okay. To compute the natural frequencies, the damped frequency, logarithmic decrement, and other things. Because this objective includes different types of damping, damped and undamped vibration case, that's why. And to find the free vibration responses using some simple MATLAB coding. Once we drive the motion equation, we can apply those equations to the MATLAB program. Then the program will provide us a beautiful picture of the condition of the oscillation. Actually, this is the kind of a small video lecture for various type of oscillations. So let's see some of them. This is the one which we have seen, that undamped vibration case. So let me this is what we have observed there in the first picture. Yeah, this is the situation of undamped free vibration case. How the undamped free vibration. So what we can see here, initially, this system is given an initial displacement from started from some point and then oscillate periodically. This is a periodic motion that continuously vibrating. Okay, this is for the displacement and this is for the velocity of the oscillation. The second one is damped case. In the damped case, we have different types of damping conditions based on the damping constant or the damping ratio. Zeta value, which is the damping ratio, critical damping conditions, undamped conditions, and overdamped conditions are analyzed in this case. So this is for the underdamped oscillation. Yeah. So let's see another type of oscillation with damping, that is known as overdamped case. Here, in this case, it is not oscillating like as we have seen in the previous case. It goes immediately and then goes very near to the time axis. Only in the first half cycle, it goes to maximum position. Immediately goes, then stops there. And we have also, this is actually critically damped case, but how about overdamped case? The situation is almost the same, but in the case of overdamped, it goes to some point and immediately cease there. So let's go to our discussion. So what is this free vibration? A simple definition for free vibration is system side to be undergoes free vibration when it oscillates only under an initial disturbance with no external force acting on it. After disturbing the system, no external force will come. That f of t is equals to 0. So simple example of free vibrations are, for example, the swing of children on the pendulum. For example, I can take some example here. For example, if I give, this is in initial position, if I give some initial disturbance, this will oscillate like this. So this kind of motions are considered. This is the best example. Child in a swing. Another one, the grandfather clock. Okay, here there is a pendulum which can oscillate like this. Okay, another, the oscillation of inverted pendulum. Here we can see the space needle and space needle structure, which so many examples can be given. So examples of vibrating system also continue. Continuum beams, okay, beams which are suspended to some walls and having a cantilever length, they can also vibrate. Okay, if we give, okay, again, rotating shafts with some eccentric mass also vibrate. Rolling ships and boats in the sea, airplane flying through the heavy clouds due to the turbulence effect of the cloud, still that vibrate. And the machine base also vibrate, especially those machines, the machine shops with heavy duty machines. Again, the structure of lathe machines and the milling machines at the time where we are performing metal cutting, then the system will vibrate. Okay, so as we know, this aircraft wings are having a long span, so the tip of the aircraft wings are also vibrate, and we can model it as a simple cantilever beam with kind of lumped mass. Okay, with the material property EI. So this is a representation for the aircraft wing vibration. Also, the ships vibrate when they are in water. So there are center of gravity, okay, meta center, center of buoyancy. Those points, when the shifting of this happen, when the boat moves in water or on the sea water level, then it will vibrate also. Everything in the world, even we consider them rigid, they can also vibrate. Okay. Even as we know, the earth sometimes vibrate. That's why we call it as earthquake. Okay. What are the inputs and outputs of the vibrating system? That is another question. So inputs are the excitations. We give initial excitation force, and then the outputs are the responses. Okay. Our aim is to find what are the responses, what is the amplitude of vibration that causes the structure for some hazardous condition. That is our intention. What are the mode of vibrations? Okay. For multi-degree of freedom system, a number of mode of vibrations are there, and which mode of vibration will easily affect the system. That is our intention. Okay. To identify the natural frequency of system, to identify the vibration and amplitude at different mode of vibration. Okay, that's what. So the response depends on the initial conditions and external force. Okay, most practical systems are very complex in nature. So, for example, if we consider a slender beam or column, it has a multi-degree of freedom system. When we talk about the freedom system, some continuous systems are infinite number of degree of freedom. But for simple assumption, we discretize the system into any number of equal parts, and then we'll make a finite element analysis on that in order to evaluate the whole system. So that mathematical modeling requires simplifications. Okay, we simplify any system. So the procedures are, as we have discussed previously, mathematical modeling is there, the deriving the governing differential equations is another, solving the governing differential equations and applying the boundaries and initial conditions, okay, and then interpreting the solution finally. So that is the inputs and outputs of our system. So actually, that's why most of the time this vibration analysis can be analyzed using the Laplace transform function. Okay, so we can give input here, and the system is here, output here, and we can make a feedback loop here. Then we can make a control system, or and then we can solve it in the Laplace transform equation. Okay. Free vibration of single degree of freedom system. Okay. So that is simplest vibratory system can be described with single mass connected to a spring, and if possible, in the case of damped dashpot also included on it. So when one variable can be described the motion or structure of the system body, then we call it as 1 degree of freedom system. Okay. So, for example, if we are describing the system in terms of x of t as a coordinate, g of t, z of t, this g of t may be a local coordinate, or y of t, then it is called a single degree of freedom system. So the mass is allowed to travel only along a spring elongation direction in this case. Such systems are called single degree of freedom system. Okay, yeah. We can see those single degree of freedom system in many places. I can show you this figure. Here it says the figure. So mechanical system, when we call mechanics as systems, according to Newton's law of motion, from the base for analyzing mechanical system, Newton's second law equation states that the sum of forces acting on a body is equal to the product of mass and acceleration. Actually, this Newton's second law is the law of momentum conservation, that force is equal to the change of momentum. Okay, change of momentum. Then that is Newton's second law. And Newton's third law, that is the law of action and reaction. Okay, for our purpose, that it states that if two bodies are in contact, then they experience the same magnitude contact force, just acting in opposite direction. So that we call it as the law of action and the reaction. So action is always equal in magnitude and opposite in direction. So this is the law of momentum, that Newton's second law of motion. So these are the Newton laws of motion. So this is the figure. Okay, spring mass system having also damper here. Okay, this is a spring mass damper system. We can produce free body diagram for the system, considering the when we apply force on it, what will happen on the links of the damper and the spring. That the spring is a representation of material stiffness here. It is not simply a simple spring, but it is a material representation. That is the stiffness of material. Now we proceed by summing up the force and applying Newton's second laws as given in the equation 1 in each direction. In this case, there are no forces acting in the y direction, so that the y force is not considered. It is only in the x direction. So this is what you call the forces for this system. This is a general single degree of freedom system. So actually damped single degree of freedom system. Okay. So this equation is known as a governing equation. Okay, it is a differential equation in terms of second order differential equation. So spring mass system in horizontal position. Let's see the spring mass system in horizontal position here. This is a spring mass system. There is no damper on it. So when the spring is stretched with some x from the initial, then it exhibits kind of motion, so that this is the free body diagram representing this system. Okay, so there is no external force on it. Okay, so one thing what we must understand is this is the point where our inertial coordinate will be taken, and the surface here is considered frictionless surface. Okay, this is frictionless surface. So we idealize many parameters like this. Okay, so equation of motion for undamped free vibration case. We have, so when there is no elements that cause dissipation of energy, then during motion of the mass system, the amplitude of the motion remain constant with time. Actually, this is for undamped free vibration case. The system vibrates at its natural frequency. Okay, so this is one of the examples of undamped free vibration. Okay, a spring mass system where the equation of motion is given like this. Okay, so this is a torsional system which is vibrating about this axis. So the torsional vibration. So here mx dot of t plus k of x of t, which is equal to 0. So mass is the inertial property which is characterized by acceleration, and the material elasticity or the material stiffness property k is characterized with the deflection or deformation of the structure. So here we consider the mass is replaced by J naught, that is the mass moment of inertia, and x of x dot dot is replaced by theta dot dot of t. Okay, and k is by torsional elastic constant kt, and x of t is theta of t. So this is the equivalent system in the torsional vibration case. This is a sliding crank mechanism, which has, we can represent this in terms of x and the theta in a combined system, but we consider this as a single degree of freedom system. This is also another idealization of tall structure, like long one-story buildings or other systems. We consider the overall mass as a lumped mass and the stiffness of the supporting structure by 3EI by LQ from the strength of material concept. This is taken from the strength of material concept. Okay, so if there is no external force applied on the system, f of t is equal to 0, there will be will experience free vibration. Motion of the system will be established by initial disturbance only, as we have. Further, if no resistance or damping is there, c is equal to 0, that means it is oscillatory motion will continue forever. But there is nothing which continue forever. We assume that. So such system is termed as undamped free vibration. Okay, so this is the governing equation of undamped free vibration. Okay, so solution to the governing equation. The solution is second order differential equation. For example, x of t is the solution for m of x plus k of x is equal to 0. This is a second order differential equation of homogeneous type, because the term here is 0. That implies the system is homogeneous. And here we can see second order differential. Okay. So this is for this we can estimate, or we can assume solution from our linear algebra concept, or the knowledge of from the knowledge of linear algebra. We substitute x of t. We assume x of t is equal to some arbitrary constant c times e to the power of st. S is some parameter that the eigen value or parameter, and time is the time marching of the system. Okay, so if this is considered a solution, then x dot of t is the velocity term, and x dot of t is the acceleration term. So substituting these three equations into actually the first and the third on this equation, what we can get is an equation like this. So here in this equation, there are two terms. One is the term inside of the bracket, and another is CEST. So to have a solution for this term must be different from 0. That is, CST is different from 0, and the term inside of the bracket, which is known as the characteristic equation, which is equal to 0. Then from that we can get S squares. Okay, so CST is different from 0. And for the non-trivial solution, the square term is can be 0. So this is characteristic equation. Okay. So the eigenvalues are the roots of the S terms. The roots of S terms are we can find plus or minus I omega n t. Why? Because here we have a minus value that leads to the complex form of numbering system, or this is a complex representation. Okay, I omega n, I indicates that the complex number, that is radical of -1. Okay, so with this, the term k over m is defined as a natural frequency. We define it as k over m is equal to the natural frequency of the system. So finally, the solution becomes, because we have two S1 and S2 eigenvalues, so that this general form of equation, x of t is equal to CEST, will be split into two from the mathematical concept of linear algebra or mathematics. So x of t is equal to C1 EST plus, I forgot here, yeah, it is EST plus C2 E minus ST. This represents S values are plus or minus I omega n. So we substitute this. Finally, we get this equation. Okay, let me use some highlights. Okay. Let me okay. So this is our x of t. X of t. Okay. So initial then on this equation we have to apply initial conditions. Actually, before going to initial conditions, we have to make some manipulation, mathematical manipulation on this. Just applying the Euler formulas for this equation. Okay, so we have initial conditions that x of t at time t is equal to 0 represented with x naught, and x dot of t is equal to 0, that is v naught, or sometimes we can take it as x dot naught. Okay, so applying this on this equation, we can find the two constants C1 and C2. Okay, we can see further, especially the relation between this equation and the Euler sine and cos for complex equations of number having this type of complex with exponential. This is exponential representation of complex number, and how we can relate it with trigonometric relation that we can see later. So the equation of motion becomes like this for such given initial conditions. Another case is a spring in vertical position. Let's consider spring in vertical position. If a particle is displaced through a distance xm from its equilibrium position and released with no velocity, then the particle will undergo simple harmonic motion. So this is the type of, this is initial position, unstretched initial position, then deflected to some delta S. When mass is added on it, it deflects like this. That means the position where this is mass times gravity is equal to K times delta S. And then after that, after this equilibrium position, then further disturbing the system, further disturbing it from this initial position to downward position like this, or upward like this, what we can get, the equation of motion for such system. So here, mass times acceleration is equals to F, which is equals to weight minus k delta st plus x, which is minus kx. Then finally, from this equation, by rearranging it, we can get this equation. Still, this is a second order homogeneous equation of the equation of motion. So this is the general form of solution for this type of motion, as we have tried to drive in the first case. So here, x is a periodic function, and omega n is natural circular frequency of the motion. Okay, so C1 and C2 are determined applying the initial conditions. So from that, C2 is equals to, actually here we used sine and cos. So C1 is equal to, no, C2 is equal to x naught. C1 is b naught over omega n. So substituting it, we can get this equation. Actually, the equation is, sorry. We can apply this to this equation. So finally, it gives us what? X of t is equals to, okay, C1 is x naught. C1 is v naught over v naught over omega n. Sorry, times sine this term, and we can, it is simple substitution actually, it's not required. So what is the behavior of this graph seems like? So the velocity time and acceleration time graph and the displacement time graph all are represented here. For example, if this is for this system, this is displacement time graph. What we are discussing here is our analysis is in time frame. It is not in frequency. I am not telling you in the frequency frame, but in the time frame. So displacement, xm means maximum value of the displacement, positive and negative maximum values. Okay. In the case of velocity, that is the first derivative of x, so that we have x omega n is the terms, the maximum, which indicates the maximum amplitude. And then for the acceleration, x m omega n square. This is xn omega n square, or this one is for the acceleration term. Okay, so this is displacement, velocity, acceleration. Okay, and these are the equations. And we can observe from here the displacement and velocity are having phase difference, and also acceleration and velocity also are in phase difference also. Okay. This is also another representation for free vibration of particle in simple harmonic case. Okay. Here we can see equation of motion, maximum amplitude. Maximum amplitude is it is the square root of C1 value square plus C2 value, or that constant 1 square plus constant 2 square gives us the maximum amplitude. And the time period of natural time period, which is equal to 2 pi over omega n. And then the phase difference between the phase angle is given by V naught over X naught omega n. That is C1 over C2 in this case. Okay. So this is the how it happened, that oscillating system. Okay. Let's take one example. An object stretches a spring 6 inch in equilibrium. So set up the equation of motion and find its general solution. Find the displacement of the object for t greater than 0. If it is initially displaced 18 inch above equilibrium and given upward velocity of 3 meter per second. So when we come to solution, it is undamped, that c is equals to 0. It is free, that f is 0, which gives us my dot plus ky is equal to 0. This is the type of equation what we have. And then another thing, in static equilibrium position, mg is equals to k delta L. Delta L is that the initial deflection, or S sometimes we call. So delta S. From this, we can find K over M. K over M is equal to G over L. So which gives us this value. Because from the given parameters, we have this thing. Yeah, actually here what we must consider is the G value in feet per second square. This is the gravitational constant, that instead of 9.81 in metric system, in feet per second it is 32. So that, and also another delta L, which is given 6 inch, which represents 1 over 2. That just keeping the consistency of units. Okay, so which is equals to 1 over 2. Okay, so delta L is 1 over 2 or 6 inch. 6 inch means in feet, it in 1/2 feet. So finally we get 64 that we can consider unit meter per second square over meter. So it is, I think, per second cube, meter by meter per second, yeah, meter per second square over, actually this is in inch. Anyways, just to remind, okay, mass in kilogram, okay, kg. So this will be meters kilogram, meter per kilogram second square. Okay. Okay. So finally, the question of motion becomes this, because once we know k over n, we can substitute in this place 64y, and the assumed solution, considering the exponential function, assumed solution becomes xe st. X is arbitrary constants. And then finally we get characteristic equation of s squared plus 64, which gives us the eigenvalues, which are 8 plus or minus 8j. This is the omega n value here. Yeah, okay. So therefore, the general solution for this x1, x2, substituting these values, actually x1 and x2 will be obtained from the initial conditions. So we can substitute this to the equation. Okay, this is the type of equation which can satisfy the given form. So initially upward displacement of 18 inches, that is positive because it is given upward, and must be expressed in, because it is inch here given in inch. So 1 inch is equals to 12 feet, I think. 1 feet is equals to 1 feet. 1 feet is equals to 12 inch. So from that, 18 inch is equals to 1.18 inch is equals to how much? From that, we can get 3/2. Okay, let's apply these points, and the initial velocity given is -3. So substitute it, and finally we get 3/2 cos 8t minus 3/8 sine 8t. This is the general solution, and this is the graph. Okay. At time t0, if we give time t0 for this system, this will be 0, and we can get, this is the point 3/2, 1.5 or 3/2. And when, yeah, so it is going like this. This is the equation, or this is the graph. Okay. Again, free vibration for simple pendulum case. Okay. So simple pendulum also an special case of free vibration approximation. So we have here frictionless attachment is there, weightless cord is there, only mass is having this ball is having mass. So it will go like this, which obeys energy conservation, that mechanical energy conservation. For example, the mass kinetic energy plus potential energy at this point is equals to kinetic energy plus potential energy at this point. For example, at the lower position, there is no potential energy, only kinetic energy is there. At the higher point, there is a potential energy, that the point at which the ball will go to the maximum up and start to come back. On that point, we have maximum potential energy mgh and zero velocity. Then it will come back. So at this point, the point at which it passes the kilogram point, there is only tangential velocity or the kinetic energy, but no potential because delta H is zero. Okay, so it obeys conservation of energy principle. Here, mgh, here half mv square, and at somewhere we have both of kinetic energy and potential energy. So the summation of energy is equals to zero. That is conservation of energy will obey. So the solution equation is in terms of summation of force is equals to ml theta dot dot. This theta dot dot is the it is a function of theta actually. So this is weight. So weight sine theta is this component. Here normal acceleration and tangential acceleration. Okay. So these components are taken. So finally we can get theta dot dot plus g over L sine theta. So here this g over L is almost equivalent to that k over m in our equation of linear system. So we consider a small theta for a small value of theta, and finally we get this equation. This is a equation of simple harmonic motion or equation of pendulum. And then we assume a solution of this type also. Theta m is the maximum value of theta. Okay, sine omega nt plus pi. Or we can represent it in terms of exponential function also. No problem. Anyways, the natural the natural time period of the natural time period of oscillation is that 2 pi over omega n, which is 2 pi radical L over G. So let's consider some techniques of used in the driving of equation of motion for vibrating system. As we have seen some techniques like Newton laws, the Lagrange form, again energy conservation form, D'Alembert principle, and others. So Newton's second law is one of the principle that we use. D'Alembert principle is also another principle of virtual displacement, that virtual displacement delta application, and principle of conservation of energy. So let's see governing equation of undamped system using equation of motion. That equation of motion implies the Newton's second law. So that Newton's second law states the conservation of momentum. Okay, d over dt md x of t dt, that is momentum, which is equal to mx dot. And actually we apply all the sum of forces in x is equal to 0. Sum of force in the x is equal to mass times x acceleration. sum of force in the y, which is equals to mass times y acceleration, and the moment about some point p in about z-axis is equals to moment about it is central axis plus some offset axis, moment about offset axis. So which is, so these are some of the systems, spring mass system and the free body diagram, and we apply the motion equation, simply summation of f of x is equal to 0, no mass times acceleration. Here we have only, when we cut it here, we can get friction, no, that spring force. Spring force is the only force here, and this is acceleration this direction. This N1, N2, this mg will be cancelled. There is no friction, because if there is frictional force, this will be different. So considering no friction, so finally we can get this equation as a equation of motion using Newton's second law. For torsional system also, this is the free body diagram. Okay, this is this disk is rotating like this. Okay, and we have J naught theta dot dot, that is the acceleration mass times. This is inertial mass, not an inertial mass, but it is rotational mass. Okay, times theta dot dot, and then the torsional stiffness T, okay, torsional stiffness T, and the angle of torsion or theta. And then finally we can get this equation for this type of system. Okay, equation of motion using D'Alembert principle. Actually, this is a special type of Newton principle that we consider inertia force and inertia moment here. So f of t minus mx dot dot t is equal to 0. This is a fictitious force. Okay, so here also this is a fictitious moment. Fictitious moment, that is inertial moment. Okay. So this is known as dynamic equilibrium equations, and applying it to the system free body diagram as given here. Okay, so this from the system free body diagram, mx dot dot is equal to minus kx. Okay, so that gives also the same mx dot dot plus kx is equal to 0. Okay, another equation of motion from the principle of virtual work. Okay. So principle of virtual displacement, or we can say virtual work. Okay, delta x is the virtual displacement. So in this case, the principle of virtual displacement states that if the system that is in equilibrium under the action of a set of forces is subjected to virtual displacement, then the total virtual work done by the force will be 0. That is the statement. So the virtual work is defined as the work done by all forces, including the inertia force, for a dynamic problem due to virtual displacement. So considering a spring mass system, okay, at a displaced position, let's see, look, this is a spring mass system here, and displaced to some x displacement, and with a virtual displacement to delta x again here. Okay, then okay, the mass is under a displaced condition. Okay, so for this system, virtual work done by the inertial forces delta wi is equals to minus mx dot dot the whole delta x, and virtual work done by the spring forces delta ws is equal to minus kx delta x. So when the total virtual work done by all the forces set equal to 0, that will give us this equation: mx dot dot delta x minus kx delta x is equals to 0. So rearranging this and removing negative term. So mx dot dot plus kx delta x is equals to 0 for delta x different from 0. Okay, and then finally mx dot dot plus kx is equals to 0 is also another equation of motion. Governing equation from principle of conservation of energy. So this energy conservation also another method. System is said to be conserved if no energy is lost due to friction or energy dissipation, non-elastic members. Okay. Now, if no work is done on conservative system by external forces other than gravity or elastic potential forces, then the total energy of the system remains constant. That is the definition. So let's see. According to this conservation of energy principle, let's consider the total potential pi is equals to u plus t, which is constant, and the du of pi, which is equals to we can make this as d. Okay, it is not partial differential, but anyways, it can be as it, no problem. So this u and the t are the kinetic and potential energies. T is the kinetic energy, u is the potential energy. So their derivative is equal to 0 because here the sum is constant. Okay, so this is the principle. For example, for this linear spring mass system, potential energy half kx square and kinetic energy half mv square. So the derivative of u with respect to time gives us kx times x dot, and the derivative of this t is equals to mx dot x dot dot. So applying this into this equation and taking out x dot. So for x dot different from 0, we can get this equation. That is obviously the equation of motion of simple undamped free vibration case, and the equation of motion of spring mass system under vertical position. This is almost similar with what we have discussed previous. So I don't want to waste much time here. And that also finally we get the same equation of motion here. Okay. So the solution for this mx dot dot kx is equal to 0. We already attempted the solution, how to find solution. But this is second, this is also second redundant. So let me pass it as it, because it is already there. We have this type of equations. We form characteristic equation from this. Okay. And then find the eigen values, and then once we get the eigen values, we define the natural frequency, and then the solution becomes this. This is in terms of the Euler formula. Okay, yeah. So let's recall Euler formula. Previously, I didn't apply the Euler formula. So this is the our equation. This is the equation of motion, which we assumed equation of motion. Then this is a power of some we can call I xt or let it be ix simply. E the power of ix is equals to it is cos x plus I sin x. And e the power of minus ix means cos x minus I sin x. That is the Euler formula. Okay. So once we know this thing, we substitute the first this term C1 times cos omega nt is omega nt plus I sin omega nt plus C2 cos omega nt minus I sin omega nt. Just applying this formula. So here, collecting the cos terms, C1 plus C2 will come, and sin times C1 minus C2 will come. Okay, yeah, this C1 and the C2 minus this come. So this is the cos and sin terms. Okay. Now let C1 is equals to just to understand the complex form of equation. Okay, for A plus IB and C2 is equals to A minus IB. So what will happen if we add these things? A1 is equals to, okay, so let A1 is equal to C1 plus C2. If we add C1 plus C2, what we can get? C1 is this one, okay, this plus C2 is this one, that gives 2 times A. Again, A2 is equal to C1 minus C2. What about this C1 minus C2 times I? Actually, here also I is there, which gives us 2 times B I square. Here there is no I, sorry, which gives minus 2B, which shows both of the results are some constants. Okay, so that we can implement A1 rather than this these two terms. A1 implies C1 plus C2. C1 plus C2 is equals to A1. C1 minus C2 I. C1 plus C2 I is represented with A2. So finally, this is the equation of motion. And we have various form of representation of equation of motion. And this is the maximum amplitude, that when we represent the equation in terms of cos or sine only, then we can represent it with maximum amplitude, so that it is A1 square plus A2 square. And the phase phi is equals to minus of A2 over A1. This is the phase. Okay. Yeah. Solutions are in this form. This is similar thing which I have shown you. Now let's apply this initial conditions. So when we apply initial condition, A1 is equal to X naught and A2 is equal to V naught over omega n. So let's substitute it here. This is one of our equation. Or we can represent in terms of single cosine function. Then we have to use the A value, that is A is equals to radical of A1 square plus A1 square plus A2 square. We have to use this, and pi is equals to V naught over X naught omega n, that is A2 over A1. So position, velocity, and acceleration. We have seen this at the harmonic motion phase. We have seen all of these things. So the position is this. even though we have various type of representation for the velocity, the position. Velocity is this, the first derivative of this thing, okay, and acceleration is this, the second derivative of position. Okay, so the velocity leads the displacement by pi over 2, and the acceleration leads the displacement by pi. And velocity and acceleration also are lead each other by pi over 2. So this is the particular solution. Actually, these are particular case. When x naught is 0, means if there is only initial velocity is given, then x naught is 0, initial disturbance is 0. Our solution becomes this one. Whenever there is 0 velocity, velocity is not given initially, it is given in terms of x naught only, then this is our solution. Okay, so these are the case. These are various alternative solutions actually. This is the same principle. So you see, which is the initial velocity, which is very tangent to the displacement graph. So this is initial displacement x naught, which is given at the very beginning, and velocity is tangent to this point. Okay, that is, this is the position plot, and this is for, so we can see A naught means the maximum amplitude, which is this value. Here A naught is this maximum value. Okay, because here both velocity and acceleration are given, and the pi is the initial phase difference. Okay, the initial phase. Okay, initially maybe this pi. Okay. So we can take this example in the next. For today, this is enough, I think. Okay, so let me stop.